Welcome everyone to Rafael Kueng's meeting. And if I may, I'd like to just tell a little anecdote. It's about a couple of years ago when we were doing something, and I forget exactly what it was. It's just this little incident. We were setting something up in the building, and it was a weekend, it was Sunday, setting it up for later. And we did the setting up, whatever it was, which I can't remember. And when we were coming up to go, a cat, one of the campus pet cats, walked into the door and went in. And I said, "No, it's nice and warm here. I'm going to stay here. You can't very well leave that cat inside." And I was at a loss because you tell cats to do right, then they're not going to do what you say. So, Rafael, I know what he did. But looked at the cat and waved at it. And what? Did this cat came out, walked out, came out the door, and let him shut it. And so, if you know Rafael, you know that he has this kind of effect, not just on cats, but on machines, on people. So, Rafael, the floor is yours.
Thank you very much for those kind words. And yeah, welcome to my PhD defense with the title Probing the Universe with Gravitational Lensing and Citizen Science. So I will talk about, this is actually my overview. So what I did, to give a short summary, I measured the dark matter content of galaxies using gravitational lenses with the help of volunteers. So before talking about results, I will introduce you to why we want to probe the universe, how you can do it with gravitational lensing, and how can volunteers help with this task. So let's start at the beginning, really at the beginning with the Big Bang. You see here a timeline of the evolution of the universe. It starts with the Big Bang, second zero, and ends at 13.8 million years, billion years, that's today. So in the beginning we have a hot, dense soup of like almost everything, and this early universe expands and cools down rapidly. And so particles condense out rather quickly, and this soup of matter and photons, it's a big soup, a dense soup, it's not transparent, until it cools down enough that the photons can now travel freely and the universe gets transparent. So this happens about 380,000 years after the Big Bang, and this is what we call a recombination. It's when the universe gets transparent. So photons travel freely, and we can actually see those photons as the cosmic microwave background. We can see them today, and it is those photons and the observation of this microwave background that leads to our current understanding of the universe, or to a big part, the lambda called dark matter model. It basically says that the universe consists of about 5% atoms. That's all the stuff we can see, we can feel, we can touch, the regular matter you all know. And it says that it's like 27% of the thing is dark matter. That's dark matter is the thing that explains how the stars move. And then we have this huge fraction of dark energy, which we don't know much about. It's an explanation for the expansion of the universe. So my talk is going to focus about this part here, about the dark matter. Okay, let's go back to our timeline. After this recombination, the universe expanded further, but there was no light source in there. So the universe was basically dark. These are called the dark ages. It's dark structure form until you see the first star. When the first star ignites in the early galaxies. Exactly. The dark ages last until first stars in the early galaxies start enlightening the universe. So from then on, our current epoch starts with galaxies which have suns, which shine, and which are arranged in galaxies and in bigger structure. So looking at one of those galaxies, this is a rare galaxy, a particular nice one, we see that most of the matter that we see is somehow arranged here in the disk. A bit is in the bulge in the middle, and a few clusters of stars are outside. If we, however, take the same galaxy but expose the image way longer, we can see such a thing. You can see the galaxy as before. Here in the middle, it's very overexposed. It's replaced by a black image of the galaxy, so you can see all the stars around it. So there are many, many faint stars around it. So we can see those stars, but we don't actually know why the stars are there and why they move as they do there. So there's not enough mass to keep them at this place. You can also look at the more common reason for the dark matter, the rotation curve. If you look at the galaxy and look at which radii, how fast the stars move, if you only consider what we see, the luminous mass, then you would actually expect a curve that flattens out. If you're going out further, it's like the planets in our solar system, the ones further out move slower. But what you actually observe is kind of different. The velocity goes up and then stays on top. So this is an indication that there must be way more mass around here than we can actually see. And this leads to our current model of a galaxy, which is arranged like this. We have in the middle the bulge or bar, and the type of galaxy surrounded by a disk. And then we have a stellar halo with stars around it. And then we have a dark matter halo, something, I don't know what dark matter is out here, which is enormous. So in this talk, I will talk about a lot about matter, different kinds of matter, and just as a reminder, if I talk about stellar matter, star matter, that's this thing in here. It's the things we see, the stars that shine, the gas, which is in the galaxy. So the disk, the bulge, and the globular clusters here in the stellar halo. If I, however, talk about the total mass, then this is everything in one galaxy. So this is the stellar mass plus this fraction of the halo mass. This is the total mass. And usually the dark matter mass is way, way bigger than the stellar mass, as you can imagine with this graph. So, okay, let's look at a few galaxies. I show you here our neighboring galactic group, our galactic group, the local galactic group, where we see the neighboring galaxies like Andromeda. If we have a look at them and if we measure their light, we can infer to the mass of those galaxies. If we plot this mass, here on the x-axis we have the mass in logarithmic scales in terms of solar masses, so 10 to the 10 solar masses. And on the y-axis, we have the amount per volume, so the density of this galaxy. So what this says is we have this times 2 per megaparsec cube of 10 to the 10 solar masses galaxies. So this is the orange curve is what we observe. In opposite to it, here on this plot, we have the blue curve, which says what we actually expect. So if we take the model, the lambda CDM model, put it in a computer, run body simulations, and then we get out the simulated universe. If we analyze this, and if we analyze the halos that were built in this simulation, and then if we multiply by the baryon fraction to get the stellar mass in those halos, we get this line here, the blue line. So what this actually says is this is the total amount of stars that could form in a galaxy, theoretically, if the process of forming stars would be really efficient. And what we can see is around here, around 11 solar masses, those galaxies are quite efficient in converting matter to stars. So the star formation in here is really as high as what we always would expect. In opposite to the low mass end and the high mass end. Here we see quite a big discrepancy. So, for example, low mass galaxies, we see way less than we would expect. And one of the explanations for this is we believe that supernova feedback plays into this role. So low mass galaxies have a really weak gravitational field. If the first massive stars go supernova in these galaxies, they eject out material of this galaxy. So material that would later form more stars will get ejected out and won't be there to form new stars. So that's why we expect, that's why we think that there are less. In opposite to the high mass galaxies, here high mass galaxies tend to have a really strong, really big supermassive black hole in the middle, which is very active. That's why we call this active galactic nuclei feedback. We think that those active galactic nuclei inject jets of material into the surrounding gas of the galaxy, and that this heats up the gas and it prevents the gas to cool down and to condense into stars. So this will lower the star formation rate in the big mass area. But those processes here, they're really up to debate at the moment. So the theory is not quite clear about those. And those are only two of several more possible processes. So it would be really nice to probe those processes a little bit better. So this plot here shows you basically the same setup with a little bit, I think, easier to understand axis. Here we have the stellar mass, as I introduced before, in logarithmic scales. And on the y-axis, we have total mass of the galaxy. Then we have this line, the white line, which is there. So everything below is unphysical, so it can't be more stellar mass than total mass in the galaxy. That doesn't make sense. So all the galaxies have to lie above these lines. And this blue line here we get by abundance matching. So it's a similar process that I already explained. By using simulations, we get what we would expect the mass fraction to be. So it would be really nice if we, and we would again expect most galaxies to lie here in this region, and the low mass galaxies here should be not that numerous as we need the high mass galaxies. So it would be really nice to have some data points in this plot. We have some measurements that we can actually reject or confirm theories with. And to measure the stellar masses, that's doable, that's what I already introduced. And we can measure the total mass of a galaxy with, my title gives it away, with gravitational lensing. Gravitational lensing helps us probe this dark matter and helps us estimate this dark matter or this total matter. So gravitational lensing is an effect of GR. So when light travels through the distorted space-time, then the light path gets distorted as well. Exactly, it was historically one of the first proofs actually for the general relativity of information. So how does gravitational lensing work? So I put here just a quick image of a regular lensing. So you have, notice from the optics, parallel rays that focus into one focal point. That's how regular optics work. But in opposite to this, gravitational lensing works a little bit different. I put here the formula for a point mass, for the deflection angle. So what you can see is the deflection angle decreases with the impact parameter. So as further away as the light ray passes my point mass with m, the smaller the deflection angle gets. This is an opposite to the regular lens, where the further out from the optical axis you get, the bigger the bending gets. So everything focuses more. Okay, there are also a few other differences. There are no, for example, there's no dispersion with gravitational lensing, but this is the most important. Okay, so I prepared a small demonstration. I hope it works to actually see the effect, what it means. If we get this one running here. So, okay, I have a light source here. And I have brought my gravitational wave and my gravitational lens. So the bottom of a wine glass is actually shaped that it behaves similarly to what I showed you before. If light ray passes like on the outer part, then it gets deflected only slightly, but the deflection gets stronger the further in you go. So when I try to show you the effects of gravitational lensing with this webcam, I hope you don't get seasick or so. Okay, maybe I should turn around. Don't burn my cable. Okay, so we have the light source, which gets in the beginning just focus a bit distorted. But if I move further in, distortion gets bigger. And if you have a look at the top, well, now the sun is not helping. But if you look at the top, you can see now, you can see at the very top, you can see a second image. And if I arrange it further, you can see like the whole ring, the flame creates like a whole ring around it. So you can see the same thing, the same flame, you can see multiple times, or even as a ring. Okay. That you can do, like, you can try yourself later on in the apero. Okay. Sorry. Okay, let's go back. Okay, so some real examples. This is one, rather famous one, and this one is one I worked with. I tried to show you that different alignment gives different configurations. So if it's only on the border of the lens, then you get a distorted image. But if you go like further in, then you get even multiple images. And this work is about what we call strong lensing. It's about the situation when we have multiple images. So there are several sources of light, like my candle. Here you see a quasar. So there is a galaxy in front and a quasar behind. And you see the quasar 4 times. Here you see a galaxy in front and some other galaxy behind, which you see 4 times. So, and I'm interested in this foreground galaxy. So I'm interested in the lens, because the light coming from the background gets distorted at the lens. So let's look at the setup in a bit more technical terms. This is a usual lensing setup. We have a source of light here, which is not super visible. We have a lens here, and we have the observer here on this side. So what light would usually do is, the vertical lens, it would travel a straight line, the green line. To the observer, we would see it here on the plane, it's the XS. But if we put a lens there, because of the distortion of space-time, these photons won't reach us. But the photons that travel up here will get deflected here at the lens, will be deflected down, and the observer, so we standing here, will see the image not on this place, but up here. And I already mentioned it's even possible to have multiple different ways the light can take, so you could also take it down here and come to us, and so on. So for lensing, we usually do a few, for this kind of lensing, for the strong lensing, we do a few assumptions. first, we assume that this distances here, the separation between observer and lensing plane, lens and source, those are huge. So our angles here get really small. So we can work with small angle approximations. That makes our life quite a bit easier. And a second thing is, if these distances are small, then we can neglect the extension of the lens in the Z direction. So we can just project the lens onto a plane and work on the lensing plane, and the same yields for the source. So we can work on the source plane, the lensing plane, and with two-dimensional coordinates, the x's and xs here, for example, that are on the lensing plane. So there is this famous lensing equation, which, if we use these approximations, is quite easily understood. We take the DOS with theta, this is this part here, this equals this part plus alpha here, this part. So this equals this. This is the lensing equation. Keep this in mind, it will come up later on. But the nice thing about this is that this deflection depends on the gravitational field. It only depends on the mass, and it depends on the total mass, not on the stellar mass, but on the total mass. So by looking at this geometry, by measuring this deflection, we can infer the total mass. Okay, so this is the tool that we can use. But first, we need to find the lenses. I mean, those setups, they have to be pretty much straight in a line from our point of view. They're quite rare. We do have some surveys going on. For example, the CFH-DLS survey, which covered 150 square degrees of sky area. It was searched intensively, and in this survey, it was found that 1 square degree had like one order of magnitude one lens. So we get like order of magnitude hundreds of lenses in this survey. Exactly. So the currently running and delivering data surveys like the KITS and the dark energy survey, they're running now, and they increase this area by a factor of 10. And surveys that are currently planned and being built increase again this area by a factor of 10. So we actually talk about not any more hundreds of lenses, but tens of thousands of lenses that we could possibly detect. But for that, we need to scan through a lot of images to find those particular lenses. And there are several ways to scan through those huge data sets. One is, of course, computers, robots, artificial intelligence. Another one is to ask volunteers to help you scan through this. It's not actually, nowadays it's called citizen science. It's not that a new approach to ask volunteers to do data analysis for you. I think the people at CERN did it a long time ago. Exactly, so one of the projects I want to present is the SpaceWorks project. SpaceWorks asked volunteers to scan through all those images and to click on lenses if they find them. It was actually a blind lens search. Part of the idea was to identify which lenses got missed by previous searches, which could have been visual searches by professionals or searches by AI, by robots. To help to evaluate the performance of the volunteers, they put some training samples inside. So they generated lenses with no parameter and put them in, and checked whether the volunteers find those lenses. So that helped evaluate the performance of each volunteer. The result was 59 new lensing candidates. They are not yet confirmed, but 59 new candidates. And I will talk about those candidates later on. But first, I want to talk about the designing phase of this SpaceWorks project, the kickoff meeting. So when project got planned was in 2012. It was here at university, and it might very well be that this story with the cat was when we prepared for this meeting. So during this meeting, the idea that volunteers couldn't only do lens detection, but could also create models of those lenses, so we can get the mass from them, came up at this meeting. But the process of modeling is quite complicated, it's quite intensive, and it was then rejected for the Space Force project, but we thought we'd give it a try. And but the thing is, since it's quite complicated, we need to get an easy way to motivate and volunteers and to explain the whole process to volunteers. So we need an easy way to input a model configuration. And we basically want to go from here, that's the survey image, to here. That would be a distribution of mass. And to get this link from here to here, we need to dive a bit into the theory and into some formula. Stay with me, it only takes a few minutes. Okay, so up here, on the one hand, we have the lensing equation that I already showed you. If we do some replacements, we actually want to work on the lensing plane here with coordinates on the lensing plane. So we do those replacements and we solve by alpha. Then we get this term for the deflection angle. On the other hand, I showed you this formula for the deflection angle of a point mass. So you see this is linear deflection angle of the mass. So if we assume an extended mass, we can basically just integrate over the extended mass. And I also already explained that we actually want to work on the lensing plane and we project the mass distribution on the lensing plane. So we actually work with the surface mass density. If you put this together, then we get this formula down here. And stay with me. If you have those two formulas, they're both for the deflection angle, so we put them together, we equate them, we put everything on one side, and then we have 0 equals something, and then we then we integrate by x, and we multiply by 1 minus z, and to get from the angles to angular diameter distances, and then we multiply by 1 minus z, 1 plus z to get to the two distances, and then we have distances, we divide through c to the speed of light to get the time. So why this is a bit complicated process? Why do we do this? We can now see that we have two parts. We have the green part and we have the orange part. The green part depends basically on the distances between the parts and the position of the source. So the green part is a geometric time. So this time is geometric, how the lens is assembled. And this part here has the mass, so the surface density inside, and this is then due to gravity, so that it's a deflection due to gravity. So the actual formulas don't matter that much. Keep in mind we have the arrival time surface, I will call it. I will explain in a minute what it is. So we have a geometric part and the gravitational part. If we go back to the plot, we see exactly. So this gives the time that a photon takes to reach us. So we have, compared to the direct connection, we have a deflection due to the geometry. So this line is longer than the green one, so it takes longer to travel. And we get an additional deflection here at the lens because the photons have to travel through the gravitational field, which leads to a time delay. That's correct. Yeah. So with this formula, we can write down a time, a light travel time, how long it takes the photon to arrive us to each point on the length plane. So in each point we can assign a time. So virtual photons would traveling through this point and reach us would take a certain amount of time. But of course we're not talking about virtual photons, but we're talking about real photons. So real photons only take halves, which are stationary. This is the Fermat's principle, which you probably all of you learned at high school. So exactly. So this is what is written here. This is actually the beauty of this formula. We already have this here. So the stationary points of the radial surface. Okay, let's try for the volunteers. We try to visualize this radial surface a little bit. So imagine we have the source on the left-hand side from your point of view, which emits a bunch of photons, a bunch of virtual photons, which travel through space and then reach us. Here we don't have the situation with no lens in the middle, and just we get the part of a sphere arriving at us with the minimum, obviously, on the straight line connection. If we, however, put a lens in the middle, then this surface here of the arriving photons, this arrival time surface, gets distorted. It can be in several ways. This one is an easier distortion, which leads to a saddle point up here and a minimum down here, and the maximum where the lens is. And there are also more complicated distortions. Actually, it's so this random surface encodes the whole process of lensing. But it's actually not, you don't need actually to consider a whole radial surface. It's actually sufficient to just look at the stationary points, so the minima, maximum, and the saddle points, and maybe to the self-intersecting contour lines around those points to help classify them. So then it's clear the topology. And so this self-intersecting contour lines, together with these points, actually classify or characterize a certain lensing situation in the geometry. So we can use this as an input method, as a starting method, to go from what we see on the screen or on the survey image, to go from there to the mass. So, okay, so this is the input we require, and I would actually like to show you the program and how it works. So bear with me. Let's see how it works. To fire it up. That's always a bit dangerous. But so okay. Okay, so when the volunteer first starts up, he gets this screen where he can enter a name, demonstration here, and then we can load the lens. This uses the same identification codes as the Space Warps project. So we use one of this, the one I already showed you a couple of times, 7K4R, and then we load this image. This is the whole sky patch that people saw in the Space Warps survey. There were like 400,000 of them. We zoom in here to our lens, which we found, and then we try to create the model. So we see the 4 points, the 4 images, and we have an educated guess. So this is the closest one down here, and then the one on the left-hand side, and then the upper one. So we expect, as I said, educated guess, this one to be the saddle point. So we place a point here, and the input works this way. You place 1 point, which is now minima, and then you can expand it into a saddle point and 2 minimas. So the input is a bit restricted, but it always leads correct inputs. So we believe that the maximum is here at the galaxy, and the second settle point should be here, and the minimas around the second settle point should be down here, and one up here. So, okay, now the contour lines are a bit messed up, so we need to clean it up a little bit so it looks nicer. And this is why it's actually called spaghetti lens, because those contour lines tend to end up in a big spaghetti mess. Oops, let's reclaim this. Yeah, okay, so this is good enough, I think. Then we can, if you already know something about it, we can enter the redshifts of the lens and set the resolution. And then we start a modeling process. And now the configuration that we entered is sent back to the server and is modeled server-side. So what actually happens, this input together with some priors restrict the solution space. And then, this is what is happening now, and then the algorithm on the back end generates, then samples this solution space, generates 200 models in this solution space. So if when I'm talking about a model, this is actually an ensemble of models. So it's like 200 or even more, you can change the parameter of models that are together build one model. So now we got a response from the server. Let's see. This is probably not a good one. Let's see the synthetic image. So the server then renders the model it creates and sends the image back. So this is a simplified rendering. It's a arrival time surface rendered. So we can see those two images are presented nice, this one as well, but the fourth image down here, that's not so well. So that should be brighter. So that would mean we need to adjust our image and then remodel and then improve it iteratively. We can also check the contour lines of the generated model and the generated mass map here. If we would be happy, then we could save the model, upload it, and then we get a link to this model. If this link leads to a result page, this can be shared in discussion forums and so on, and then people can discuss about their creations and their models, and they can even, if they find one, if they find a good one, but they would improve something, they can here down just click and revise the model, and then the whole website loads up and loads the model in it, and we can revise the model. So this is the basic system. Let's switch back here. Here. Right. Okay, so this is the layout of the whole system. Really quickly, you request the model, the server gets it from a data source, stores it, returns it back to you. Then you start working on, you create a configuration for a model, you store it to the system, and then you ask for a rendering of the model. So if the rendering is not done, the server kicks off a task that creates the model, and then it's stored back in the storage system. And then you can finally get your model, and then you can either revise it or you can go out and share it with other people and discuss about it. So one of the nice things about this sharing is that it leads to a tree of models. And I have to be honest, this was actually an idea of one of the volunteers. So we have a tree of models. When you can improve on models or revise models that were already created, this is a nice way to explore the different models, the space of different configurations that are possible. So we find this is a quite nice thing. Here's another view of a more populated model. Unfortunately, you can't see the numbers, but each point is a different model. That's from a collaborative modeling effort of one of the candidates I showed you before. Here I show you the total amount, the total number of models generated for all those candidates from the SpaceWorks project. So the 59 candidates from the spacewalk project. We gave them to our volunteers and asked whether they could create models from all of them. And this is logarithmic space, so attention. So I tried to keep it small because it was still in development most of the time. So this is the contribution of about 8 people, of about 8 modelers. You can see there was quite a big kick here in the beginning when we started it. This was this modeling effort, the 3 I showed you before. And then here I put online a revised version and asked people to complete all the missing models. So this was another kick. And finally we got something, we got 377 models in total for the 59 candidates. One candidate didn't get modeled because it was quite hard to be modeled. Okay, we did, of course, also test the performance of our volunteers, and we did it use the same training sample that the spacewalk project used, so that the previously generated simulations, the simulated lenses, and we showed them to the volunteers and asked them to model a few of them. And for the simulated lenses, we know the actual Einstein radius, the lenses they used to create the lenses, and we compare this to what our volunteers recovered from the images. And you can see that, so ideally, the result would lie on this dashed line here. You can see that we have a slight overestimation here. This was one of the early versions of the program. That's why I did a reversion and put online the second version afterwards. Exactly. You can see here the gray band is the performance, or is what an expert modeler would get. So I presented this gray band. You can see that's actually quite good. There's a bit of variance, but the volunteers are quite good in there. And now I will get to this plot, back to this plot. So as a reminder, we had here stellar mass of galaxies versus the total mass of galaxies, and we wanted to have some points in this plot. And actually, what we did is we used those models that were created for the candidates, and we, together with the volunteers, selected for each candidate, selected one favorite model. And we plot this favorite model on here. So this is the result. Each model, each candidate is represented in a square. So the error in the lensing mass, the total mass. Okay, first. First I have to talk about it. Now the caption changed from total mass to lensing mass. So the problem with lensing is that we don't sample the whole dark matter halo. So we only get a fraction of it. So what we expect is that our mass, the lensing mass we measure, has to lie below this line. It should be somewhere below, and obviously above the logical line. And yes, and we see the error in the lensing mass. So this is the error that is generated when one ensemble of model is generated. So this is from the least massive model to the most massive model in one ensemble. This is the error in the lensing mass. And the stellar mass, the error is quite big here. So we use the linear method, the crude method to get the first estimate on the stellar mass. That's we only fitted one band per magnitude, so the brightness of only one color was fitted to get a stellar mass, so it is only as an estimate. That's one part where Philip is working on to improve this error here. So we are looking forward of having those rectangles more like having squares than this distribution. But the overall picture we see is is quite nice. We see that most of the galaxies lie in here, in this region where we expect them to be. We do have, however, some outliers. Let's first talk about the low mass outliers here. So this outlier is a bit a sketchy one. So our diagnostics for this model is not that convincing, so we're not sure whether this model is a good model. This, however, is really convincing. The image looks nice, the mass distribution looks nice, everything looks really nice about it. And if it's true, that would be a quite a remarkable galaxy, which is really on the low end, low mass. So we really recommend this for follow-up observation, for example, with Hubble or whatever is available. Same for this one up here, so the really massive one up here, that might also be a really interesting one to look at. Yeah, but otherwise we do have now some measurements of lensing masses. We hope to get the stellar masses better. So we do have some measurements, and we can now throw the ball back to the theorists that can try to try their theories with the feedback theories of galaxy formation with this data. And with that, I would like to go to the summary. And yeah, as I already said in the beginning, we did build a program with a novel input method that allows volunteers to help me to measure dark matter content of galaxies. So this is that. Maybe I finish with a quick outlook. We hope that we can, the space warps will continue to run with the second run, and that would be an ideal with the DS data, so that would be ideal to also get our numbers up by an order of magnitude, the numbers of created models. And with that, I would thank you very much for your attention.
When you teach the volunteers what is a good model, do you like explain them in every detail what is a good model, or do you leave some room there so they can explain?
So that's actually a good question. The volunteers always ask for methods to evaluate how can they be sure that the model they created is a good one, and that's a tricky point. So we work on a few improvements that I didn't show you here. We have a better synthetic model which actually uses the light on the image. Maybe let me quickly go to a slide. Or not? Ah, here, this one. Okay. That uses this light and then inverses the lens, projects it back on the source plane, and then averages all those images, and then does it reverse again, lenses it again, and then you can see the image. And if this, so this would be a better way of assessing the quality of a model, if this back projection, taking the average on the source plane and then projecting the average image of the galaxy we get on the source plane back. And yeah, but we also work on other measurements in the latest paper we try to publish. We have some measurements that the volunteers can tick, so whether it's, are there any, if there are any other galaxies nearby, then this might complicate the process of modeling and so on. So we are still working on ways to give the volunteers better feedback of how good the model is.
From these images, are we
how do you get the distances, for instance, from the source to the lens interface?
We measure the redshifts, basically. And, well, to be honest, so our process is we can rescale the whole thing. So we have default redshifts of 0.5 and 1 if we don't know it. And because at first we didn't know it, and when the Galaxy, the SpaceWorks people released a paper, they had the redshifts of the lenses that were published there. So we use those redshifts for distance from observer to lens. From where the source lies, we don't know exactly. We put it far away, that redshift 2. This might sound a bit crude, but this can be easily rescaled afterwards. This is a formula can do a transformation. All the values can be refined. It's already in the pipeline. As soon as we know better values, we can put it in, and then we get better results. No, it's more we're waiting for spectrums to be taken of those things. So it's a bit hard to get telescope time. But as soon as they get observed, then we know better.
You mentioned that the data set which you are analyzing now as a science project had been analyzed previously by professional astronomers and also by robotic methods. Now you found quite a number of new lenses. Do you have some understanding on why they sort of fell through the mesh previously?
Well, so the robots are usually good at recognizing what you train him with, or what you train it with. So robots usually find lenses that are quite similar to those trained and in quite empty fields with high signal to noise. Yeah. So if you have noise, then robots tend to get bad. And I think the sample that SpaceWorks found was quite diverse. I'm not sure whether you want to add something to it, but I think that's the point.
On the spaghetti lens example you gave, and you showed the same lens just a minute ago, there's a blue blob right at the edge of the frame. Could that be another image?
That's one thing you could try when you have the software as a volunteer. You could try, but you can somehow get this into the image. It is, however, probably not an image, I would guess, because the thing is there's nothing else around here, much else around here, and there is the odd number theorem, which says that images only come up in odd numbers. So that's why the input, I didn't explain it in too much detail, but that's why the input works with adding 1 point and then you expand it into the 1 into 3 points. So it can only be an odd number of images. And if there is one here, there must be another one somewhere. Or it must be 2 images that are really close together so we can't distinguish them. The model works way better if we do it like this. So that's why I don't think it's an image belonging to the system.
Where are the odd numbers of images here?
Sorry?
Where's the odd number of images here? It looks like an even number to me. Just how do I count?
Okay, yeah, that's actually. So the last one, the missing one, is here at the maximum, which is usually very faint because it's the maximum, and it's usually by order of magnitude outshined by the foreground lens galaxy. So it would be here, but you can't see it. But so you usually expect the maximum to be in the lens from the time delay of the backwards field. This.
Just go ahead.
Yeah, so could you use AI to model that now? Obviously, the human being is better to find all these answers. But
Yes, that's a good question, and there are actually papers coming out like this month. 2 papers, or last month or this month, 2 papers came out that tried to do modeling with AI. So far, they weren't really good. So for really clear situations, easy situations, they can do it, but most of the time they fail. So yes, that's a good point. I actually prepared a slide about the whole AI thing. Okay. Oh, I deleted it.
This job
Or did I? It should be here. Okay, never mind. Yeah. So if you look at, there is a famous AI contest. It's called ImageNet contest. And if you look at the evolution of the AI from like 2012, 13, 14, 15, 16, they really make huge progress. So the detection rate of stuff goes from like 10% to 70%, and the error rate of identifying stuff drops down from like 70% to 20% or even less. So AI does do a lot of progress. And yeah, I can talk about a lot. I think the space warp's kind of approach to do things, it's in a bigger context. So the space warps is a sub-project of Galaxy Zoo. And they basically do those tasks, the classification, identification things. They do it a lot. They have like, a lot of projects going on. And I think they will get steamrolled by the AI development. I think they always do the same. And I think that's not the way citizen science should progress. So you should get your volunteers more challenging tasks, because the AI will catch up soon, or even is catching up now. That said, I think mine is a bit more challenging task. And the thing is, I mean, the AI research takes like 5 years, 10 years to catch up. So AI is now ready-ish to identify images, and the first tries started with doing models. But this data is data here. That's now here. We have to analyze it now, or we can analyze it now. We can't wait another 5 years or another 10 years for the robots to develop to be good enough. So yeah, I think for this project, time is on our side, because we have the data from those we have now, and we have to analyze it. And this is a method that now is here and now works, instead of waiting for the robots to evolve to a good enough state.
well, you could actually, your results you could feed back into the AI.
Yes, you could use them to train robots, of course. I think that's another aspect. I think that might not be the best thing for citizen science. I'm not sure how. I don't have any data about the motivation of citizen scientists, but I think one of the key points is also that they can see something that no one has ever seen before, and they can possibly contribute something by finding something. If their task is basically train a computer to do your job faster and better, I'm not sure whether volunteers still go for this. Maybe they do. Maybe you could turn it in a game, and you train your robot and it has to compete against other robots or something. Maybe that works. I don't know. I'm a bit skeptical. I would try to keep it I would not to try some gamification aspect into it, but keep it with science. Because I think it's also really nice. Citizen science has the aspect of outreach to volunteers, which is a really nice aspect, and I would keep it really serious and don't put a competitive aspect into it.
Just one more thing for the moment. I'm very interested by your M star M lambda plot right at the end, sort of the key results plot, particularly the outliers you pointed out at low and high mass. So this is the one, yeah. So at the very low mass there you have a stellar mass of around 10 to the 9, maybe less, and then a lensing mass of 10 to the 11. So that's now right on the blue line. And there's several others that are also lying along the blue line. Now, so if the true mass is larger than the lensing mass, they would then move off the blue line, and that would invalidate this abundance matching that you mentioned right at the start. So in order for them to be consistent with abundance matching, then for those objects on the blue line, the lensing mass must be very close to the actual halo mass. So is there something about them and their images that might lead you to believe that that's the case?
So, yes, maybe this band shows that the span between two different age trends that we assumed for that. So this one would assume a very young stellar population, and this assumes an old one. So I would guess that for this it's more it's an older one.
Sure, but even for the old stellar population one, that would put you on the blue line. You can't afford to have the halo mass be any larger than the lensing mass. That would move you above the blue line, right? So is it the case that for, I guess what I'm driving at is, are the lenses on the blue line, do they have much more extended images than the typical lenses? I mean, if the typical physical scale of the images is similar to all the lenses, then I would worry that the true halo mass of that object on the left is much bigger than the lensing mass, and therefore it's going to be a problem for abundance matching.
I would ask the question: is there a blue line? Right? I mean, is there actually a blue line in abundance matching? Do you? Well, so I mean, so of course that's the mean abundance matching, but all abundance matchers basically put in a scatter usually of about a factor of 2. So there isn't really a blue line.
That's from one particular.
Yeah. So this abundance matching is I actually don't recall. This is one particular. So the math.
Is there a tendency with some these extreme examples, if you can recollect anything, is there any indication that you're looking at the full halo or nearly the full halo, or you're very close to the surface in the alpha?
To be honest, I don't recall. I would have to look through the images.
It might be something to look at. If that were the case, then you might become convinced that for a certain subset, you are actually getting closer to the halo mass, and actually therefore better able to test the abundance matching of that subset.
Yeah, I was just wondering, how is it possible to exclude the possibility of multiple sources? Do you have to have enough spectral information to do that? Or you can't see the source, so you're just looking at the images, and how can you exclude multiple sources?
We could look at follow-up observations, but at the moment I think we can't. But it's the probability of multiple sources.
Probably aren't very many, but I just wondered.
Yeah. But with the survey data, like just with this, I think we.
Just to chance lines.
Yeah, basically, yeah.
There are, okay, I suppose according to the work, according to the diagnostics, you said what is the morphology?
Um, um, sorry. I would have to.
You can say it's probably more likely.
Yeah, it's unlikely, but to rule it out.
The sources are like clusters or something behind.
Any further questions? If not, we'll continue with the second part, which is the closed session.